Good morning. Thank you so much for having me. I'm Chandra Krintz. As Sandeep said, I'm from UC Santa Barbara, a professor there. I'm here with my colleague, Dr. Rich Wolski. We're both computer science professors. And today, even though we're talking to you about the convergence of IoT and big data, we have in our past lives worked with startup companies and transferring technology out of the research lab into industry as part of cloud systems. My company is called AppScale Systems. Rich's is called Ubiquitous, which was recently purchased by HP. So today, analytics, as we all know, is why we're here talking about it, is driving our economy. It affects all aspects of our economy and a wide variety of companies, but it's really seen tremendous success in the web services space, in the e-commerce space, and in social networking, where these companies are collecting vast amounts of information about us to help us and provide us with better services, but also to extract actionable insights that they can use for marketing, for advertising, as well as to sell us more things, to recommend things that we want to buy or people that we should and want to meet. And what's interesting is that these analytics have really turned us into tremendous consumers. And so I'm here today to talk to you about whether we could use these same technologies to turn us into tremendous producers, food producers. If you think about the ag industry today, it is completely underserved by technology, let alone analytics. Now, there's some technologies out there, some precision farming, some sensors that have emerged, but it's really hit and miss. Yet the area is really important to us as a society. We have to feed 9 billion people by 2050. There are 7 billion now, and we're not doing so great. So it is ripe for improvements, and we, in our past, have brought technology to bear to solve hard problems like this, through efficiencies, through automation, through increases in productivity. So the ag industry is really important to do this with because there is no more land. We can't just expand and have more farms. There's the amount of arable land in the world is done. We've used it all. And so that means, and then again, our resources are really limited, so we're going to have to do more with less. So efficiency is going to be where we make our inroads. And this area is ripe for analytics because they already collect tons of data, all kinds of sensor information, historical records. Farmers keep it manually, logs manually, but there's also government and federal and state agencies that collect information that we can use to understand how our farms are working and what we might do to help them improve their efficiencies. The commercial opportunity is huge. The amount of food we produce in California alone is enormous, 50 billion last year. Hopefully, we need a little more rain to maintain that this year. But again, it argues for the fact that we need to start acting now. And then worldwide, I believe this is the key to emerging markets. So in terms of analytics then, we need to make Amazon recommendations to farmers for things like irrigation scheduling or the application of inputs, fertilizers, pesticides, water. We need Google search for crop disease. We need Tinder for pests. I was giving this talk in North Dakota about a month ago and talking to a bunch of farmers, and there was a bunch of ranchers and milk producers there. And they're like, but we need this too. It can't just be farming. You know, we want to use this type of technology in our milking systems. And I said, okay, we can do that, but we're just going to have to call it Moogle. So technologically, this is a very exciting sort of convergence of areas that are really thought of as independent. And researchers traditionally have focused on them independently. So it's IoT, and I'm grouping in, sorry for you robotics people out there, I'm grouping in robotics with Internet of Things. There's the big data side of things. The machine learning is really important at this point. Statistical analysis is going to be vital to make good decisions on the farms. And then image processing, where we can use multispectral imaging to understand our systems without going in manually and gathering this data. So my group, Rich and I, work on the systems that are at the cross-sections of these technologies. How do we bring these technologies together efficiently and in a way that makes the most sense to solve problems in the domain of farming? Here's an example. So in the top left, what you see is a bunch of samples taken from a field. This is just a graphic displayed from ArcGIS. And what our colleagues at Fresno State did here is, this is a field of wine grapes, and they took a handful of samples of the grapes. It's near harvest time, and they wanted to identify which grapes were high quality and which grapes were low quality so that they could control a differential harvester, a tractor, an intelligent tractor. And so what they did is they came up with a really interesting interpolation algorithm that could separate the yellow parts, the bad grapes, from the dark parts, the good grapes, so that the harvester could automatically put the good ones in one bucket and the bad ones in another so that it could produce wines. And they did a really amazing job with this. You see a little squares on the display there. On the left is a little tree in the field, and in the middle is a little well. On the bottom right, what you'll see is we took the same data as part of our SmartFarm effort, and we did a diffusion analysis to try to understand not how to control a tractor, but why this differentiation of quality was happening. So we applied this a diffusion analysis technique to figure out the root cause, the likely root cause of this issue, and we were able to nail that down using the same data, completely independent of the other work that was done. So you take data and use it in lots of different ways. Once you have something like this, you can hand the farmer an iPad, and they can, instead of walking the entire field, they can focus their energy to find where the problem might be. We don't know what the problem is, but we have a very high confidence that it comes from this location on the field. If you want to be more sure, you can fly a drone over your fields. It happens all the time now. Great companies are working on this to take multispectral images of the crops over time, and you can watch how your crop is changing in terms of the plant's health and identify when and where the problem starts to occur. You can also use this type of imaging in terms of using the thermal spectrum to identify where leaks occur, because leaks have an area that has a little bit different temperature than the rest of the field. So there's really easy ways that we can combine lots of really interesting technologies to solve some of these problems really efficiently. So the work that we do in terms of the research fall into 4 key areas that I think need new computer systems advances. The first one is in this hybrid cloud approach. There's certainly going to be things that you're going to do in the public cloud. There's lots of data that's shared across our United States, let alone our state, that we could make use of. But there's also lots of data being collected on farm. So it's unclear whether you want to transmit tons of information off farm in order to do the analysis on it. So we believe that the right solution is a combination of the two. If we're going to put some computation on farm, the system that we develop there must be lights out, easy to use. It must be self-managing, must be completely fault tolerant, must be like a TiVo box. You turn it on, it just works, right? And you don't need a system administrator. That is the goal. How do we design systems to enable something like that? The system on farm and in cloud must run all of the popular analytics, and it must be adapted to any new analytics that come up, because we're going to want a vast diversity of our population to contribute apps to this cause. And if you write your app in Hadoop, if you write your app in Spark, then or R, MATLAB, all of that should work in the same system, transparently, portably, on cloud, on farm, wherever the system is. So we work on problems associated with these types of functionalities. Here's what it looks like. So we have a farm. We collect all kinds of information about the soil, about the plants. We take imagery data. We have farm records. We have lots of really interesting information. Most of our farms are lucky if they are connected to the internet. And if they are, it's extremely low bandwidth, and it's very expensive. Satellite, cellular, it's ridiculous. And it's not the whole farm that's connected. It's a building on farm. So we have a connectivity problem that we're going to have to address. And it argues for putting some sort of computational power on farm, I believe, so that we can gather and aggregate and summarize this data to make these, to extract these actionable insights for farmers. And it gives us the choice then. If we want to move the data to the cloud and perform analytics there, we can. And if you want to move the code, which is much smaller, to the farm, to the data, we can do it there. So to enable that type of portability, we leverage our past work in cloud technologies so that anything that runs in Amazon and anything that runs in the Google Cloud Platform will run on this appliance, right? So it doesn't matter where you run the analytics. It will run either place. You now get to decide where it makes the most sense to do so. We have an App Store model so that if you're going to compute on farm, people who contribute apps can download the apps to the data and perform the analytics there. So our appliance, think of it like a refrigerator. You don't ever look inside, you don't ever look behind the scenes, but you use it and you know that when you open that door, the light comes on. We build it out of NUCs, Intel NUCs. We have a dumb switch. We have 6 boxes now. It's a full-fledged distributed system, 24 processors, over a terabyte of disk. Right now is when we have about 100 gig of RAM, wireless tower, so we can connect IoT on farm. $4 grand. $4 grand is what it costs now for that box. Full-fledged distributed and parallel system. We then designed a system so that we can run all the different analytics. Now, there's a lot of challenges associated with this because most things, Hadoop, Spark, Storm, they think they're running by themselves. And so they compete for resources in really interesting ways. And so we work on research problems associated with how to keep these guys from beating up on each other, but yet having the benefits that they all bring to the analytics table. The systems themselves were kind of turning cloud on its head. These technologies like Spark and Hadoop and Storm and even AppScale and Eucalyptus were designed for super large scale. They're high availability, super fault tolerance. Now we're shrinking it down. We're going backwards. Right? We have fewer processors. We have a smaller distributed system. So we can leverage all of that high availability and that fault tolerance to make this a lights-out appliance. And that's how we're changing the technology into something new. We lose a box, it's fine. The thing will still continue to run. We lose a few pieces of components, doesn't matter. The intelligence, the new thing that's here is that we build the configuration and the reconfiguration and the top fault tolerance that this requires. So one thing I really like about UCSB computer science department in particular is that a lot of us have participated in sort of startup companies, and we have partnerships with industry, and we've always worked closely with industry. It's always been really supported and promoted in our department. And so one of the things that really drives our research is our ability to use these partnerships, to leverage these relationships so that we can perform real validation. We aren't just sitting in our labs making this up. We are out in the fields. We are working with partners. We talk to farmers and growers all the time. And we can only do it with the support of amazing startup companies, as well as large-scale big industry players and new and emerging IoT and sensor companies. So in summary, what we think is that growers need ubiquitous innovations. These systems have to be super easy to use. I think it has to be a combination of on-farm, off-farm, on-farm, and cloud. What's really important, and I've kind of brushed over it here, is that farmers need to be able to control their data. All the value of what farmers own is in their data. And that's why companies love to take it for free. And we want to develop a model that gives farmers control over their data. If they want to share it, great. If they want to sell it, even better. If they don't want to do any of that, then that's great. We've got to give farmers choice. And if you talk to real farmers, that's important to them. It's got to be super inexpensive. Super inexpensive. Open source software is going to be key. Hardware's got to come down in price so that this becomes viable. It's all happening today. We are at the point where this makes sense. And it has to be effective. It's got to solve real problems that farmers have. We can't just make up problems. We have to go to them and we have to ask. And that's what we do in our lab. So, of course, we can't do it without an amazing group of students and lots and lots, a huge army that came before these guys, but also with our collaborators and sponsors who have now given us the ability to really focus on some of these really sticky and hard systems problems. But I have to say, in the end, we can't do it alone. We have to develop a community if we're going to feed the planet. So please, come join us.